Before I begin my prepared remarks, I thought I'd just make an observation. There's a sub-theme that's going on here today in some of the speakers, and it relates to sort of the canonical concept of canonical circuits or commonality in the cortex. And none of the speakers took the extreme positions, but the extreme positions as outlined by Gary, on the one hand is, there's no commonality, everything is different, and we have to figure out every little circuit in the world. And the other side is there's one canonical circuit in the neocortex, and it works for everything. No one believes that, although after Sebastian's talk, you might get really depressed, because I think by the end of this talk, he was going to say there's 50 bipolar cells in the retina, and it's going up every hour. But Gary was taking some position a little bit to the right of that. As a theorist, and I'm a theorist, our job, and a theorist's job, is to try to make complexity look simple. And the goal is to try to figure out commonality and how to take all this complexity and put it in some sort of framework. And you have to act that way. Of course, you don't believe it's always that simple, but you have to take that approach. I think it was Einstein who said you have to make things as simple as possible, but no simpler. And so in my talk today, I want to let you know I'm going to be talking in absolutes about simplicity and structure that we think is common throughout the cortex. I don't actually believe it, that as I know about the complexity, I know about those differences, but I'm arguing for a framework in which to see as far as you can go. The role as a theorist is to say, how far can you go with common principles before you have to give in and say, okay, there's variation going on here. So just bear that in mind during my talk. I'm doing the job of a theorist. I'm not ignorant of all the things that people talked about. Okay, with that in mind, let's just get going. Let's see what my time is here. Okay, so the title of my talk is Reverse Engineering the Neocortex. Let me just tell you about what my company does, Numenta. We have a primary mission, and the primary mission is to reverse engineer the neocortex. Sounds pretty simple. Some people laugh at you saying that, but we take that very seriously. That is our primary mission. If I couldn't do anything else in life, that's what I'd be doing right now. If it didn't relate to machine intelligence or technology, I'd still be doing this. What do I mean by reverse engineering the neocortex? We want a biological theory first and foremost. This is not biologically inspired. It's not biologically plausible. I care greatly about the neuroscience and everything about it. We spend our days reading neuroscience papers, discussing every possible part of the neuroscience literature you can imagine. It's quite detailed biologically. On the other hand, it wouldn't be a theory if we didn't have an information theoretic and a mathematical understanding as well. It's not just a categorization of how things are connected and what does that tell you. It's like, well, what are the information processes going on here? So you have to marry these two things. Great detail in biology. I'm not saying you have to do this. This is what I do. Great detail in the biology with theoretical constraints and trying to understand what's going on. The way we test our theories are two ways. We test it via the neuroscience, and we test it via simulation. It's surprising that in our work, we come across, this is not surprising, we come across many, many testable hypotheses as we go along. What is surprising, you can almost always get the answer by digging into the neuroscience literature. Everybody talks about getting new neuroscience data, but the vast, vast majority of neuroscience data that's been collected over the last 100 years has been unassimilated into any theory. And so you can almost always get the answer to a question that you didn't even know someone actually might have studied if you just go back and look. And we do that, and we were able to falsify our theories quite often by doing that process. And we also run simulations, very detailed simulations, to make sure this stuff works and we're not fooling ourselves. I'd like to tell you that I feel we're making great progress on this. I'm going to share that progress with you today, and it's accelerating. This is not something that's going to happen in 50 years or 500 years. It's happening right now, and I'm very confident about the work we're doing and how things are picking up, and I'll give you my roadmap as we go along. Now, as I said, if I did nothing else in life, I'd be happy doing this. But I also believe we have a second mission, and that is to be a catalyst for machine intelligence. I only say this because I believe machine intelligence is going to be based on neocortical principles. I felt this way over 30 years ago when I fell in love with this field. I can't believe I have to argue for this point, but I still do. That, the way to build intelligent machines is to understand how the brain works, how the neocortex works, and once you understand those principles, you can build machines that work on those ideas. I think a lot of people want to believe that. They just keep getting beaten down, and they keep trying to give up after a while. I haven't given up, so that's what we're doing. our goal is not to do a whole brain simulation. Our goal is not to even build anything human-like. I have no desires to pass the Turing test or even think about that. Our goal is to just build machines that work on the principles of the neocortex. They're going to be very different than any kind of animal that's ever existed, but they're going to be amazingly cool. And of course, we can build machines that are larger and faster and have new senses and new embodiments. That's where the excitement of machine intelligence is, not passing the Turing test. Okay, so that's the background of what I do. I'm now going to sort of give you a state of my view on where we are in neocortical theory. You're going to hear one person's perspective about going and doing that. I have to just start with a few basic premises. I know most of you know this, but it's worth reviewing this stuff again. The cortex is a memory system. That's how I view it. It interfaces to the world through a set of sensors. Those are sensory arrays. The retina is not a sense. It's a million sensors. There's a million fibers in the optic nerve. There's a million fibers coming from your spinal cord, about 30,000 from your auditory system. Those axons are identical. The action potentials on those are identical. There's no light, sound, or touch entering your brain. It's just patterns. And this is one of the arguments for canonical circuits. It's a very fast-changing stream. Let's remind ourselves that. My speech is changing the pattern of activity in your cochlea every 10 milliseconds or so. Your eyes are moving constantly. Total change of rapidly changing patterns every few times a second coming on all your senses. This is a rapid, high-velocity data stream coming in that's very parallel. Of course, the cortex doesn't just sit there and listen to it. The cortex acts on the world. All high-level behavior, actually the cortex controls the other parts of the body which makes behavior, but we'll assume for the moment that the cortex is controlling your behavior. So my speech is coming from my cortex, or when I move my hand over here to pick up my phone. This is also a stream, a high-velocity stream. I'm generating very precise patterns in time right now. This is not a spatial pattern problem. This is a temporal pattern problem. Now, one of the things, of course, is if you think about what's happening, most of the changes that are occurring on your sensory data, most of the changes that occur from your retina or from your somatic senses are because you are acting in the world. You moving your eyes. I'm hearing myself speak. The vast majority of the changes that you experience on your sensory, that this velocity, these changes, are because you're moving in the world. Not all of them. You're listening to my speech. You're not generating that. But you're turning your head. You walk down the hallway. You go to the bathroom, whatever. And so the brain does not... Its world, the changes coming on its sensory are largely dominated by your own behaviors. So what we say the cortex does, it learns to model the world primarily through behavior. It's sort of an active learning process. This model is time-based. We've heard that term referred a few times. Everything we do is about time-based patterns because that's what the cortex has to do with. And it's a predictive model. I think Tyson Lee was talking about earlier today as well. So it's constantly predicting what's going to happen next. Okay, we want to understand how this system builds a model of the world because when you're born, it doesn't really know about everything and it has to learn about everything through this process. How does it do that? So I'm going to start with some cortical facts. Remember what I said earlier. I know this is much more complex than this. I'm looking for simplification. So I've shown here at the top a picture of a human neocortex, a rat neocortex. Pretty much everything I'm going to talk about today is independent of the species or the size of the neocortex. We're looking for those common elements. It's a sheet of cells about 2.5 millimeters thick. It is, depending on your point of view, remarkably uniform. This struck a lot of the early researchers, and of course, if we dig deeper, we see the differences. But it is remarkably uniform anatomically and functionally. It's very difficult to put your finger on one part of any cortex and say, oh, wow, that's radically different than some other part. It looks remarkably uniform. Of course, it is organized in a hierarchy. And the hierarchy would become complex. I don't really care about that. It's organized in a hierarchy. So different regions in the neocortex are connected together in a hierarchical fashion. And how complex you think that hierarchy is doesn't really matter. It's hierarchical. The first thing you're going to see if you slice through the cortex in that 2.5 millimeters, you will see layers. They're visible under a visual microscope, an optic microscope. Now, the number of layers doesn't really matter here. I'll get to that in a moment. But you do see layers. We typically... It depends on how you count them. There could be anywhere from 4 to 10. I'm just going to talk about as if there are 4 today. You see these cellular layers. The next thing you're going to see is that the neurons are aligned in little, I'm talking about mini columns here, little columns. Now, mini columns are physical. They exist. That's been proven over and over again. There's a large debate on whether they're functionally useful. They're a process of development, so they're there, but basically neurons are aligned in these very skinny columns, about 110 neurons each, cutting across all the cortical layers. We believe they are functional in a way that's different than most people think about. Of course, you get one step further. You see the neuron itself. This is a pyramidal cell. About 80% of the excitatory neurons in the cortex are pyramidal cells of one type or another. And they have a lot of synapses, 5,000 to 10,000 synapses on them. Actually, very few people have counted them, so it's a little bit unknown. But we do know it's in that range. A good estimate is about 8,000 synapses per pyramidal cell. One thing we now know is that we know that the excitatory synapses on a pyramidal cell are not on the body. They're not on the soma. They're on dendrites. They're all on dendrites. Some are close to the cell body. Some are further apart from the cell body. And we now know that dendrites are active processing elements. A lot of this work started with Paul Rhodes, who's in the audience here today. But what that basically means, if I have a single synapse that becomes active on one of these dendrites, it has very, very little effect at the soma, or maybe non-observable. But if I have a certain number, between 10 and 20, that become active co-located within a short distance, about 40 microns, it can have a very large effect. It's not a linear thing. It's a binary type of thing. You can generate different types of spikes and MDA spikes. And so these dendrites act like little coincidence detectors. They're not just summing up at the cell body. And finally, learning, people tend to think of learning, we heard a lot of it today, as modification of synaptic weight. But there's a different view, is the one we hold to, which is learning is all about rewiring. It's about forming new synapses all the time. This is a much more powerful type of learning. It has a much higher capacity for learning, and it turns out it's necessary in the kind of models we build. We know this occurs in real brains all the time. It doesn't mean that you're throwing away all your connections all the time. Your body is pretty settled at this point in time, but we do know this is occurring all the time, and that is how we model learning in our models. Okay, so I call these cortical facts. We'd like to understand how they work, what's going on here. We have a very basic framework, theoretical framework for this, which you heard the term earlier today, hierarchical temporal memory. It's pretty simple. Essentially, you have a hierarchy of identical regions, mostly identical. Come back to that. What we speculate is that most of these regions are about learning sequences. It's all about time-based memory. And what's happening as you go up the hierarchy, regions are trying to build a predictive model for the time-based patterns that are occurring as information comes in. If they're successful in making predictions, that you end up with more stable representations higher up in the hierarchy, sort of like a name of a song, and this occurs over and over again, so you get higher stability as you go up in more invariance, and then information flows down the hierarchy, you kind of unfold these sequences. So that's the basic concept. I don't view that as very speculative, given the brain really has to be dealing with time-based patterns all the time. The questions we want to know is, well, what does a region do? What are these layers doing? What are the individual cells doing? How do I understand that structure? Because if that really is the structure of the cortex, that's the thing we have to figure out, how this works. Okay, so let's just jump in a little bit further, and this is we're getting to where our theories come into play. Here's a picture of a slice of the cortex. Again, I'm showing 4 layers of cells, layer 2, 3, 4, 5, and 6. I know it's more than that. It's a good way of framework for starting to think about it. What we speculate is that all the layers, everywhere you go, and it's really sort of segregated by layer types of cells, is doing some form of sequence memory. And there are variations on the theme. They can be quite significant variations of theme, but they're all dealing with time-based patterns. And to deal with the time-based patterns, you have to learn sequences, you have to infer them, you have to predict them, you have to recall them. And so if you think about sort of typical classical view of the cortex, one of the primary inputs is layer 4. What people think about is layer 4 gets a sensory information, but it also gets a copy of motor commands. And so people forget about that. It's getting what they call an efference copy. So when your eyes move, the superior colliculus sends literally the actions split, and they send up to the visual cortex, telling the visual cortex what motor command was just executed. And this, as far as we know, is happening everywhere in the cortex. So what we think is going on in layer 4, we think layer 4 cells are building a sensory motor model of temporal transitions. It's basically trying to predict what new inputs can occur based on the behavior you just executed and what you're currently looking at. This has to happen in the brain. This was figured out by Helmholtz many years ago. This must be a dominant thing that's going on in the cortex, sensory motor inference. We believe, you can think of that as like when you move your eyes. When you move your eyes over a face, you're not going over a repeated pattern. It's not a particular order you're repeating all the time. So you can't predict what you're going to see just because I'm looking at an eye. I can't say I'm going to see a nose next. But if I know what I'm looking at the left eye and I know I'm going to move in a certain direction, I can predict what I'm going to see there. Some patterns in the world are not because you do them yourselves, because the world is changing. And the only way to understand those is through high order sequences, where you can make a prediction based on some history of time going up to that point, like a melody or like my speech. And we believe this is going on in layers 2, 3. And these are the two primary forms of inference that are occurring in a brain. And it has to happen in every modality. We know that and that predicts that layer 3 becomes one of the inputs to the next layer in the hierarchy. One of the things that layer 5 cells do, the large intrinsic bursting cells in layer 5, is they send an axon down someplace subcortically to generate motor behavior. So when the cortex generates behavior, like my speech, it's layer 5 cells that are doing that. So this too has to be a sequence. We have to play back motor commands that are sequences, and that has to be happening in layer 5. There's no other place for it to occur, so that's the type of sequence memory there as well. And layer 6 is the most complicated of all the different layers. There's many different cell types there, but it does generally has various types of feedback, and I'll just leave it aside and just call it attention for now, and I won't speak to it further. Okay, so then the next question, I want to remind you that all the things I've just talked about here would apply to all sensory motor modalities. It's nothing specific about vision and hearing or touch or anything like that. It's pretty generic, and as far as we know, every cortical region has these basic functions. That may not be true, but as far as it's been determined so far, that's what people believe. Doesn't mean there's not other things going on, but these things exist, as far as we know, everywhere. Okay, so the question is, how would one implement sequence memory in the cortex? And I'm arguing you're doing sequence memory in all these different layers. Well, how would that come about? Well, we spent a lot of time studying this. The first thing you have to know is a little bit about the neuron, because you have to have a sense of what neurons really look like. Most neural network models that exist today have a point neuron model. We've seen a lot of these. Deep learning networks are like this. You have some number of synapses, relatively few, dozens maybe, 100 at most. There's some sort of combination. You take the inputs, multiply them by weight, you sum them together, and learning is by modifying weights of synapses. A very productive model for many years, but unfortunately doesn't look at all like biological neurons. The biological neurons have thousands of synapses, as I mentioned, maybe 10,000. They have these active dendrites we talked about, and those active dendrites act as coincidence detectors. It's as if a cell doesn't recognize one pattern, it can recognize 100 patterns. This is a completely different way of thinking about a neuron. It is not taking one thing and saying, here's the input, I'm going to process it. It's actually detecting many, many, many unique patterns in the neuropil around it. And it's literally hundreds of unique patterns that it can recognize. Some will make the cell fire, and many of them, most of them will not make the cell fire, but they'll depolarize the cell, which is priming it to fire, which is a form of prediction. And we know, as I said earlier, that learning is by growing new synapses. At least that's the most powerful type of learning. So when we model this stuff, we had to come up with a model that reflects the properties. Oh, I mentioned one more thing I should just mention. Sorry. The inputs to a particular neuron can be segregated into 3 different areas. The feed forward, what you consider a classic feed forward response property of the neuron, generally comes to the synapses near the cell, the soma. Then there's feedback onto the apical synapses at the top in this picture. And then there's actually most of the synapses are on these basal distal dendrites, which are some sort of context nearby. So you can sort of break the input of a cell into these 3 different areas. We model something, we have a model neuron, we just call it HTM neuron for no better reason, because it's part of our theories. And we model these parts of the neurons which we think are most important. We model the fact that we have thousands of synapses on our artificial neurons. We don't model the dendrites exactly. We just have an array of coincidence detectors. So we'll have an array of these guys. Each can have 40 synapses on them. And we can break them into feedback and basal distal and feed forward. So there's a sort of an active dendrite equivalent. They recognize hundreds of unique patterns. And we learn by modeling the growth of new synapses. Now, obviously, there's many, many other things that people think are important in neurons. This is what we think is important in neurons. This is the most core structure of what neurons are doing. It's not the thing on the left, it's the thing in the middle. Okay, now how would I model this? How would I build a sequence memory using these neurons? We figured this out. I'm very confident we've got pretty much the basics down. I don't have time to walk through it completely in this talk today, so I'll just give you a flavor of it. Basically, we model a layer of cells at a time, in that layer, there are mini-columns still, because the mini-columns cut across all. We might have a typical simulation for us will have 2,048 columns and 32 cells per column. So each one of those little dots would be one of our neurons. What happens here is when an input comes into the system, it creates a sparse representation, but it's a sparse representation in mini-columns. Essentially, all the cells in a mini-column share a common feed-forward response property, which is, well, it's seen pretty much, well, not everywhere, but most places people will acknowledge that. So cells in mini-columns have a similar feed-forward receptive field. And so if some unpredicted input comes in, I would have this sparse activation of columns. However, in context, if I had a prediction of what was going to occur, I have the same set of columns that are activated, but some of the cells are depolarized, they fire first, and then you get a much sparser activation. So this is an activation of a particular input in a particular context. And that's a basic mechanism we use throughout this. I won't walk through how this all works exactly, but just giving you a flavor for it. How does a cell make a prediction? Here's just a picture of a bunch of neurons in one of our simulations. The little cubes are all little neurons, and you have the red ones are active, and there's obviously a sparse activation. There's relatively few are active, and most are inactive. And what happens is when a cell becomes active, it wants to predict its own activity in the future. So it looks for cells that were nearby or available via its dendrites that it can form connections to. And it says, okay, look, these 4 guys here would be more like 10, 15, or 20. These guys here were active right before I became active. I will learn to form synapses for them. So when I see that pattern again, I will become depolarized. I'll predict my own activity. At any point in time, you'll have some set of cells that are active and far more that are depolarized. You can actually, when the cortex makes a prediction, it's predicting many things at once, and it doesn't get confused. We can show that. So you have constantly making predictions of what's going to occur, multiple things, and it can tell when one of those things doesn't happen. Okay, I'm just going to jump to the conclusion here. We have a very precise model how this works. We've been testing this for years, extensively characterized, and we can model a layer of cells. It has the following. This is what it does. It basically can learn and infer and recall high-order sequences. It is constantly predicting the next inputs. It's making multiple predictions at the same time. It detects anomalies very quickly. It says, hey, if one of the things I predicted didn't occur, I'll know that. And it has these attributes. It's very high capacity. Even a small section of as I said, like a 2,000 column section of a layer can learn millions of transitions. We've tested that. It's all based on local learning rules, which is nice. It's fault tolerant, amazingly so. You can literally drop out close to 50% of the cells or synapses, and the thing will work nicely. The way it degrades is up to a point of catastrophic failure, but up to that point, the way it degrades is it starts generalizing more. It starts losing the ability to see things separately, sequences as separately, or patterns as separately. So it just starts seeing things as more and more common. So it has a very nice graceful degradation. There is no sensitive parameters here. All the parameters work within fairly wide ranges, and the ones that have biological equivalents are within the range we find in biology. So I'm just going to state that. This is very well documented. Many people have implemented this now independently of us, so it's not like a mystery. I claim, and just to try to be provocative here, but I believe this, that this type of neuron, I'll just call this, the HTM neuron, but something like this, and this kind of cellular layer are the essential elements for machine intelligence. That these are the building blocks for building machines that people are going to say are truly intelligent. And therefore, if you're interested in building hardware for machine intelligence, you need to support these kind of structures. You're not going to get there with point neurons. And you're not going to get there if you can't learn via connection and connectivity. And you can't get there if you can't model these type of these structures. So that's just my claim. Here I'm going to share with you our research roadmap. Tell you where we've been and where we're going. So we started off by trying to understand how layer 2, 3 learns high-order sequences. That's the simplest layer. That's the layer that has the fewest cell types. It's the simplest connectivity. All the cells are primarily connected to each other in that same layer. We did that over the course of the last 4 or 5 years. I'll say from 2011 to 2013. We worked on this intensively. When I say the theory is 98%, that's just my own pure heuristic, how I feel about it. So take it as you want it. It's extensively tested in many different ways. We've put it in commercial products. We've built this stuff. We've optimized it. We really understand this very well. Last year, since the time I talked here last year, we started working on sensory motor sequences. How do I make predictions when my patterns are being generated by behavior, not by high order sequences in the environment? And we made a lot of progress on this last year. We basically took the same basic theory that we used in layer 3. And what we added in was we added in a copy of an efference copy motor command to the basal distal dendrites of what would be equivalent to spiny stellate cells. And we changed a few parameters on the learning algorithm, and it works very nicely. We've characterized it. We haven't put in anything commercial. We haven't taken it beyond that. I put a less confidence here, about 90%, because there's some things that we're still working at, but we believe we've got the basics of how this works and how those two layers, layer 4 and layer 2-3, work together. This year is the year we're focusing on motor sequences. We started really January 1st. We set down a gauntlet at our company and said, okay, we're going to really just focus on this completely. We have some of the major building blocks in place. We understand some of the big concepts about how cortex would generate motor behavior, how it would generate goal-oriented behavior, how it would adjust that behavior in the context of inputs. So when I do a behavior, I don't just execute a behavior. It's constantly being adjusted by what I feel from the proprioceptive and my somatic senses. And how do you accommodate all that? So we're working through this. I'm happy with the progress we're making, but we have a long way to go. There's some big things we don't understand as well. So that's what we're working on this year. I'm now going to switch to this part of my talk. We were told that we should be talking about applications in this meeting today. I don't think anyone's really done that, but I'm going to talk about it a little bit here. I don't say no one did it. A lot of people didn't talk about it, but maybe some people did. I don't know. Anyway, this is what we've been. We want to do applications partly because we want to test the technology and partly because we want to get people interested in it. Really, that's it. We're not charging for any of the stuff we're doing. We're giving it away, actually. We started with layer 2-3, the ones we understand the best, high-order sequence memory. Now, this is a system that has no behavior. It's just like having an ear attached to a body that you can't move, okay? I realize this is a small part of what the cortex does, but it's what we had characterized, what we understood best. So he said, let's see what we can do with high-order sequence memory. And so literally taking this model of a layer 3 cells in mini columns and applying them to real data problems. So it's suitable for anything that has streaming data, anything where you can measure something repeatedly and that thing is changing. And so we can do predictions, we can do anomaly detection and classification of temporal data streams. That's what we can do with this technology, and so that's what we've been applying it to things. So how do we apply it to something? You take a data stream, you run it through something we call an encoder. Now, an encoder is just like a sensory organ. What it is, it takes some measurement, like a number or a date, or I'll show you in a moment, GPS coordinates, and I turn it into a sparse distributed representation. And once it's in a sparse distributed representation, I can feed it into the HGM model, and it doesn't care what it is. I don't have to tweak it. I just got to get into a sparse distributed representation. There's lots of sources of data streams. So, the Internet of Things, servers, applications that there's tons of things you can take measurements off of on a regular basis. It's not so easy to get that data in reliably, but there's potentially a lot of sources here. We've built a number of encoders that are sort of generic for numbers, categories, date, time. We now have one for GPS coordinates. There's a company called Cortical did one for words, which is very interesting, but I'm not going to talk about today. So once you do that, you can build something. Now, when I was here last year, we were just introducing this product. I'm only going to show it here just to remind you, this is our first flagship use of this technology. What we did is, it was a product called Grok, and what we can do is we take metrics off of servers. So we were using AWS, Amazon Web Services, and so any server that's running on AWS, we can read all these metrics from it. We feed them into this model. It builds a temporal model of the data. The HCM has no idea what the data means, but it's very, very good. It turned out it's extremely good at detecting anomalies. And so it can detect very subtle changes in repetitive data. So in this case, the blue line is a chart of some metric on a particular server, and this happened to be a very repetitive metric. It did something every 5 minutes or once an hour, I'm not sure. And yet you could see that at one point there was a little glitch in that data, and that's when the model said this was unexpected, and that colored bar is a way of indicating anomalies, that this thing is an anomaly. You can have very noisy data, unpredicted data, but it's still predictable to some extent, and we have a very fine way of saying, well, has the predictability changed? So here again, you can see it picked up on one of those. Sometimes it's very often can detect anomalies before something fails, and so that's really useful. And it can detect anomalies that people can't even see. Humans can't see. This has worked out very well. This is a commercial product. There's people using it today. The value of doing this, let me just state the value. The value is automated model creation. That's the number one value. In just a matter of minutes, you can create hundreds or thousands of models. You just set them up, say, send the data in. You don't have to do any tuning or tweaking. You don't have to tell it what they mean. The other thing is it's continuous learning. It's an online learning application. I didn't mention that earlier, but all the models we have are online learning. So these models are adjusting constantly with every new data point. There's no training period. We basically just have to start feeding the data to the models, and after it gets about 1,000 data points, they start performing pretty well. But it continually updates, so if a particular metric changes and now there's a new characterization, that's fine, and it works. And this is a key part of this, because in this kind of data in the world, these things are always changing. And then it detects sophisticated anomalies. When I was here last year, I talked about this Cortical I/O application, a company in Austria that has taken our concepts and our models and built sparse distributed representations of words and some really cool things. I'm not going to talk about that further because I talked about it last year. It's very, very cool, but that's progressing nicely. In the last year, since I was here, we decided to do some more demo applications. So I'll just briefly run through some of them. We wanted to see, could we detect anomalies in human metrics? So people sitting at their computers typing and file access and so on. And it turns out you can. You can detect when people start behaving differently than they normally do, what you might call rogue behavior. So here's an example of someone who created a large zip file. They never did that before. We don't know that they're creating a large zip file. The HTML algorithms don't know. They just said this is not a normal pattern of metrics, temporal metrics for this particular person. It's all temporal-based pattern recognition. We did an encoder for GPS. And this is really cool. And we did this for demonstration purposes, where we can take a GPS location plus velocity and turn it into a sparse distributed representation. And we can do this, I won't tell you why, I'm just going to tell you it's clever, how it works. And it works anywhere in Earth and space. So basically we can take any point in the entire universe practically and encode it into 500 bits. And it has all the right properties where if you move a little bit, the representations just change slightly. So we tested this out ourselves. Here's someone driving to work, and the first time you drive to work, this says, I've never seen this pattern before. It's anomalous. The second time you start saying, I've seen this before, and by the third time it says, yeah, I got this. This is normal. And so it quite quickly learns what in the normal pattern, you can put this on a truck, a car, a person, a kid, a dog, material, whatever. What can it detect anomalies? We didn't program it to detect any particular anomalies. It just says if anything is different. So if you deviate from the path, if you've never done that before, it'll say that's anomalous. If you stay on the path, but you go reverse direction in the middle of it, it'll say that's anomalous. Here is me walking to the coffee shop on the left here from my office in Redwood City, California, and I go different ways, and so it says those are all fine. But if I get in a car at one point and I start moving faster, it says that's anomalous. We call it the abduction scenario. It didn't happen, but I actually did get in a car, but it was all by plan. This is being used by a company in Europe who's applying it to monitoring ships in harbors. So trying to see like, okay, can I just monitor? All these ships are going around. If I just track where they're going, I'll build normal models of what's normal behavior. And can I tell when all of a sudden the ship is acting differently? And yes, you can. It's very cool. So they've taken that. We're building another product which we're going to introduce some between now and mid-year. It's a full application. This is not a demo. And so you'll be able to download it and use it. We're going to make it free. We're going to put the source code out there. We're just using it for demonstration purposes. But what we're doing is we're allowing people to sort through all these publicly traded companies to see which publicly traded companies are acting anomalous at this point in time. And we're using 3 metrics. We're using stock price, stock volume, and Twitter volume. And we can detect temporal anomalies in any of those metrics. And then we can correlate them. And very often what you could do is then very quickly you go down and read. It's a really cool interface, the way you can look at the tweets associated with any particular point in time and see what people were talking about. It's a very quick way of finding out what's going on. If you're a salesperson, you have 20 different accounts you call on, you might want to track those 20 companies and see, or if you want to track your competitors in a market space, something like that. Again, we're doing it for demonstration purposes, but it's a pretty cool app, and anyone wants to see it, I'll demonstrate it to you later. Now, one thing I want to point out is all these applications use the exact same code base. We didn't tweak the algorithms one bit. We didn't even recompile them. There's no, basically, if you can get your data into a sparse distributed representation through the sensor, you can feed it into this thing, and it works very nicely. Okay, we try to be very transparent about our research. We have an open source project called NewPick. We have, our algorithms are documented. There's been multiple independent implementations. Our software is open source. We just made a recent decision. We're going to put everything we've ever done in open source. So we haven't done that yet. We did only the algorithm stuff. Now we're going to put everything up there. Even our daily research code is online. Some people follow that stuff. We have active discussion groups. This open source project is 2 years old. Here's the growth of it in the last year. It's almost tripled, but over doubled in the last year in almost every metric we have. So there's quite a few people around the world pretty excited about this and trying to participate in various ways. My goals for 2015, we want to make progress on goal-oriented behavior, this layer 5 cells, so we'll see how far we get on that. We really are also working on another thing, which is incorporating feedback to apical dendrites. That's a big part of what's going on in the cortex as you go down the hierarchy. We haven't been really good about publishing our work in peer-reviewed journals. We're going to get really serious about that this year. We want to grow our open source community. And finally, we have a bunch of partnering opportunities. We've been working with a group at IBM out of Almaden. Winfried Wilke's talking tomorrow. He'll talk about that a little bit. But we've signed a little joint study agreement with them. So they've been working on this for a year. We're working closely with them. We're also working closely with Cortical IO in Austria and a few other people. I just want to end my talk here just saying my point is progress is being made in reverse engineering neurocortex. And I feel very confident about this. I feel like we're getting at some of the core principles here. I understand the complexity. I understand I didn't talk about that here today. But you've got to have a framework in which you can then understand that complexity on top of. So I'm very pleased with how this has been going. I've made the argument that neocortical principles will be the foundation for machine intelligence. That's not the same as machine learning. You know, I'm nothing against deep learning networks. I just don't think they're on a path to machine intelligence, and that's what I'm shooting for. The key items you need to be shooting for in the cortex is it's an online learning system. The point was made earlier today. It's completely sensory-motor integration. Those things are not separated. They're one and the same thing in the brain. And this extreme flexibility we get out of the neocortex. You can argue that maybe the neocortex isn't as uniform as I talked about, but you can't argue it's not extremely flexible, that it can learn so many things that we were not evolved to do. Amazing number of things. And that's one of the most potent arguments for common cortical algorithms that wasn't mentioned by Gary, is how flexible the cortex is, not just by rewiring the optic nerve, but just what a normal human can learn. That's an amazing thing we didn't evolve to do. And then I made the argument that neuromorphic hydral will need to support those neocortical principles, primarily neurons of active dendrites and thousands of synapses, and primarily, secondarily, learning through changes in connectivity as opposed to changes in synaptic weights. And that's it. Thank you very much. I see I have
I'm the closest one. I like your talk, and prior to your talk I heard a lot about feature extraction, feature binding into high-level concept and representation building, and in your paper there was none of that.
Well, you happy about that, or you're disappointed?
I'm happy.
Okay, well, then I don't have to say anything.
But it's very tightly bound, the sensors and sensory motor layers and motor layers are very tightly bound. So, but what would you say to those who might be unhappy?
Well, look, there's a lot of people unhappy with what I do. You know, I could step on a lot of toes up here. You know, I don't know how to answer that question. You didn't ask me a very specific question about a particular thing. I'll answer it very broadly. I think, you know, everyone who works in brain theory and brain science wants to get at the same thing. We all want to understand how the cortex works, how the brain works. We just have different approaches. And in the end, I believe that these approaches all have to come together. So, I look at the work that like Sebastian was talking about this morning. I think it's great. It's pretty far from what we do right now, but I think these things all have to come together. So I don't view this as an adversarial community. I view this as a community we're all trying to achieve the same thing. We just don't agree about how to get there. And so I've just given you one particular point of view.
First, let me say that I totally agree with you about extreme flexibility. I think that's what's most missing in machine learning. So I wrote a piece in the New Yorker about can Super Mario save AI? And the point was that if you could build a system that could learn arbitrary new games, that would be impressive.
I remember reading that.
DeepMind went a step in that direction. In another New Yorker piece, I wondered aloud whether you would, with this system, be able to play chess. So I said, if you can do real-time predictive analytics, chess would be a nice domain to explore. And I guess I'll phrase it in terms of neocortical principles and simple as possible, but not simpler. So I accept that the principles that you have up there are right, but how do you know if you've got enough of them? So like compositionality, which is important to linguists, isn't up there. How do I know what's the break point when I've got these, but I might need some more?
Well, Gary, in your talk, you kind of addressed this a little bit yourself. You were talking about, hey, maybe I agree that primary sensory cortexes are similar, but maybe when I get to prefrontal and entorhinal or whatever, they're not. I'm with you on that one, right? We do know that as the higher up you get in the hierarchy, you get more. There's still commonality. They're still both the same neuron. They're still the same structure, but we know that temporary memory is in prefrontal cortex, not down in sensory cortex. And so there's there is this. I do agree that there are things when it comes to language. I'm totally with you. I could say, okay, fine. Look, I want to understand language as a variation of what I presented here, or something on top of what I presented here, but I'm not going to throw away this. I don't think these principles go away when I understand language. Maybe they're not sufficient, but they're going to be a foundation which to build upon. Now, to answer your question specifically, how do you know if you have enough? It's a very interesting question. The only way we can do this is we set very many strong theoretical constraints on what we're trying to achieve. So it turns out that, to do the sequence memory I talked about here, we spent 5 years figuring out how to do that. Now, why did it take 5 years? There's lots of ways you can do sequence memory, but we set out a set of requirements that are very, very difficult to solve. It had to be distributed. It had to be worked with a layer of cells that could be of any size. It had to use local learning rules. It had to be online. It had to do this, 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 and this. I had to be able to extend sequences and truncate them. I had to have, we set out a whole set of theoretical principles, and then to solve them is extremely difficult. And when you get an answer that solves all of them at once, you can be pretty damn certain that you got the right answer, because you just solved 25 constraints or 10 constraints, and that's very, very difficult to do. Now, it doesn't mean that there aren't other things that are important, but you're pretty certain there isn't another way to do this. I feel that way. There's not another way to do this. And since we've been able to solve all of our constraints, I'm able to move on to the next problem. It's not I'm sitting there going, oh, crap, I don't know how this thing's going to learn. No, I've solved all those constraints. It's time to move on. So that's how we do it. It's a set of theoretical constraints, and can you solve them all?
I'll just add one sentence, and I should yield the mic. But maybe the place to meet in the middle relates to my answer to Conrad's question about motor. So I think you're right that some of the general principles that apply in sensory apply all the way there. So for me, the question becomes, if we have this set of principles that are probably very old evolutionarily, and then we have a couple of things like compositionality, they're clearly more sophisticated in humans or mammals or something like that. What's the relation between them? I think that's a really
that's a tough one. The language you use, like compositionality, is something I just don't use that stuff. So I'm not thinking of that plane that you are. So I think it's a good way to figure out how to get these things to go together, but I have no idea. Right?
Hi. So 2 questions. So the first question is to do with the fact that you are starting to think about motor and action and so on. Yet I think this community tends to be a little bit, cortically chauvinist, for lack of a better word. So what about spinal cord? What about periphery and so on? Where does that all play a role in what you're doing?
So it's a great question. I've mentioned this briefly in the talk. The cells in the cortex, those layer 5 cells that generate motor behavior, none of them project to muscles. None of them. They all project someplace subcortically, sometimes called central pattern generators. So they project to the spinal cord, they project to the brainstem, they project to the superior colliculus, they project to various things that have a motor related. And the basic theory is that the cortex sits on top of an existing organism. The existing organism has behaviors already. When you walk, it's not cortex. When you retract your arm, it's not cortex. When you chew, it's not cortex. The cortex actually has to learn that those behaviors exist. It doesn't know that. It has to model them. The world to the cortex is not just the world, it's the rest of your body too. And so it basically models the rest of the body and says, oh, I have a representation for walking, or I have a representation for moving the tongue, or for moving the eye. And then it has to associatively learn to control that. So it sends the axons from those layer 5 cells will project down to the more distal synapses on, let's say, cells in the superior colliculus. So the superior colliculus moves the eyes. And most of the time your eyes are moving, it's not cortex at all. It's just the superior colliculus is doing its thing. But the cortex can say, would you please move the eyes over here right now? I'd like you to fixate here. And the lower structure is always in trumpet, because if the door is open here, your eyes are going to turn that way anyway. So it's all about how the cortex learns to control existing behaviors, not how it generates behaviors independent of that stuff. So that's how I view it. And then if you look at the hierarchies in the cortex, one level in the cortex actually, if it's generating behavior, it sends a copy, those layer 5 cells sends a copy of its motor command to the next higher region. And so the next higher region actually has to learn how to control the region below it. So it's from region to region to region, then to subcortical, and then subcortical, that kind of thing.
I see. And the other question has to do with the HTM algorithm. So it reminds me a little bit of the latent Drexler allocation algorithm, right? Which is strictly a, kind of machine learning, something from...
What was that algorithm?
The LDA.
Yeah.
So it has that similar kind of flavor. So I'm wondering if one can make that argument that this is an implementation of it. So
I can't answer. I don't know it well enough to answer that question.
Okay.
Sorry.
Thank you.
You argued against point neurons, and then it looked to me like your dendrites were little point neurons.
Yeah, that argument's made a lot, that, hey, isn't a dendrite just like a point neuron, and therefore couldn't I model a pyramidal cell as a set of point neurons? And perhaps you could, although you have to realize that the learning signal propagates back up through the dendrites. So there's a more intimate connection than you can get with most neural networks to say, oh, I have a soma and the dendrite, and those are just both point neurons. Because I want to train on the dendrite when the soma generates the spike. And there's a complex interaction between those two. So if you incorporated that complex interaction, then sure. I don't see why you would do that. Why don't you just design the right structure from the start? But, is it hardware implementer? Maybe you could get away with that. You could say, okay, I'm just going to, like a Karlheinz chip has a bunch of these sort of independent dendritic segments. Well, if he can map them correctly to a soma, then that could work.
So they are point neurons,
I
but
don't
with
call them point
non-local,
neurons
but they're with non-local learning rules, basically.
If you want to call it that way, fine. I think it's a very misleading way to say it, because most people won't understand all those differences. But if you want to call it that way, fine.
Actually, I had the same question. Could you emulate structured neurons by collections of point neurons? But this has been answered. But something else, in your model, are spikes a requirement? Can you only realize the spiking neurons, or are there other ways?
That's a great question. I didn't talk about spikes at all.
Right, exactly.
Yeah. Well, first of all, we didn't walk in saying, we started this, we didn't say we have a hypothesis about spiking. And spiking is a very complex topic, as you know, all different types of spiking models. Here, we model what we need theoretically. So one of the things we need theoretically, and this has been shown to be true in the cortex and neural tissue often the very first spike matters a lot. In fact, you can do some very sophisticated like image pattern recognition, and the time it takes you only have time for one spike per neuron. There's no time averaging. So in our cases, we're relying on very precise timing differences between when the neurons fire and that's really just the first spike. The second, we also rely on, I didn't talk about here, but we think we're going to rely on the difference between a mini burst and a regular spiking. So if sometimes a neuron will generate 3 to 5 very short bursts, very short spikes together under certain conditions. And so I was talking to Paul Rhodes about this on the flight out here. If you have the sort of correct apical input, questionably whether it's also true on the basal dendrites. So we need that. We need a signal that tells whether the cell was predicted before it fired, and that fits that model. So we wouldn't model it as a series of mini spikes. We would just say, I know the cell from a software implementation. I know the cell was predicted before it became active, but that would be the equivalent of a mini burst. At the moment, we are not modeling rate encoding, which almost everyone does. Now, it looks like rate encoding might improve the performance of the network a little bit. but not substantially, because these are distributed systems. Everything is distributed, we're talking about here. So the rate of a particular neuron is not really as important as which neurons are active. So from a software point of view, it is much easier to model the cells as being either active or inactive, or active with the prediction or not active. And we haven't found practically a need yet to implement anything else beyond that. We haven't found a shortcoming of any of the models we built or any of the systems we've tested where we say, oh my God, we have to add spike rates here. Just haven't had it yet. And so there's a lot of evidence suggesting in many situations it's not required, and we have theoretical reasons why it's not going to make much of a difference, so we haven't done it.
Okay, thank you.
Yeah. Okay. Thank you.